Hello, this is part 8 of a unit on comparing and contrasting linear and exponential functions, and this is the first part where we're finally getting to doing some actual comparing and contrasting, in particular for the graphs of the linear and exponential models of the population growth of Austin, Texas. That's the main comparing and contrasting we're going to do of the graphs of those functions. So the main focus is going to be to review the formulas that we got for those two different models and review how we used plot, table, ListPlot, and show in Mathematica to display what's going on. Here was the situation. Austin, Texas grew from 790,000 in 2010 to 885,000 people in 2013. We wanted to estimate the population in the year 2020. The linear model, you can pause the video and look this over, was this particular function, approximately at least. 790,000 people was the initial population, plus 31.7 t, 31.7 was the slope or rate of change in thousands of people per year. And we used that function to estimate the population in the year 2020 to be about 1.1 million people. What about the exponential model? That was down here further. That was just in the last video, part 7, where I finally introduced the exponential model. This was the general formula for this situation. You take the initial population, which I called P sub 0 or P naught for short, and you multiply it by some number b, some fixed number b to the t power. T is the independent variable. B is called the base of this exponential function. We used the other data point, the population in the year 2013, to figure out what b was. We got about 1.03858. It's probably too many significant figures, but I'll go ahead and go with it for the value of b. This was our exponential approximation. We estimated that to be about 1.153 million people. If you round that, that would round up to 1.2 million people. It might be better to think of it as 1.15 million people in this case for our estimate of the population in the year 2020. We'll go back to the linear model. I'll estimate that as 1.11 million people instead of 1.15 million people like we got with the exponential model. Alright, what I want to do now is I want to re-go through some of the Mathematica code, remind you how it works so we can ultimately compare these two graphs. Here I had entered the original linear model into Mathematica. This is a new function that I'm defining that I'm calling f, though in this video I'm going to call it f1 because there's going to be an f2 that will be the exponential model. Remember, function arguments or inputs in Mathematica must go inside square brackets, not parentheses. The variable, the independent variable, the input for these functions must first, when you define the function, have an underscore after them. That is essential. You can put an equal sign here. I like to put a colon equals. Don't worry about why. Alright, that is going to be the linear model. What about the exponential model? I'll call that f2 of t. By the way, once you've defined the functions, you don't use the underscores anymore. Okay, so I'm defining these functions for the first time. Remember, the formula for the exponential model is 790 times 1.03858 to the t power. That's the formula I'm going to type in here now. 790, the initial value again, times 1.03858 to the t power. And that function will be entered. Semicolons, by the way, just suppress output. I actually don't need them here, but I sort of do it out of habit. Table, recall, was a command that creates lists in Mathematica. They can be lists of numbers, lists of points, lists of graphs even. The convention with the iterator inside the table command, in this case I'm calling it I, is that it starts at some number and goes up to some other number in increments of 1 unit. You can change the increment if you want, but the default is to go up by 1 each time. What am I creating here? I'm creating lists of points. Points can be thought of as lists with 2 entries separated by a comma. In this case, the first entry I'm thinking of as being a t coordinate, but I'm calling it I. And the second coordinate I'm thinking of as being a p coordinate of the graph of f1 in this case. So table is going to create a list of points on the graph of f1. If I change the f1 to an f2 and do another table command, that will create a list of points on the graph of f2. I'm going to store those lists in 2 variables that I'm calling points1 and points2. I don't have a semicolon after the second line here, so I will actually, when I enter this, see the output of the second line. I will see the list points to. Watch, it will change. Ready? 1, 2, 3, go. There we go, it changed. If I put a semicolon here, it would just suppress that output as well. I wouldn't see any output, but if you do enter it, it would be stored in points 1 and points 2. Two lists. I can retype points 1 and points 2. Watch it. Ready? 1, 2, 3, go. Points 1. You see the same list that I had from a previous video. That's the points on the straight line graph. If I change points 1 to a points 2 and enter that, I will see the points on the exponential growth curve. Ready? 1, 2, 3, go. There they are. They're different points. There's nothing stored in points 3. If I change it to a points 3, I won't see any list of points. Nothing. I just get points 3 spit back at me. If I change it back to a 2, I'll see the points that are on the exponential curve. I can display those points nicely with something called table form if you want. This is not necessary. It just looks nice. Let's make that an F1 right there. Enter this. You see the points on the graph of the straight line. If I change points 1 to points 2 and change F1 to F2, then I'll see points on the graph of F2, the exponential growth. Ready? 1, 2, 3, go. Okay, if I change this to points 3, I won't see anything. No table there. ListPlot plots lists of points, like points 1. You can give those graphs names. This I'm going to call plot of points 1. There's nothing at the moment stored in plot of points 1. If I enter that, nothing comes back at me except the name of the variable itself. But if I now enter this ListPlot, it will automatically store the graph itself in the variable called plot of points 1. That's now entered. If I go back up here and enter this, I will see the graph. Ready? 1, 2, 3. There's the graph. I can also store a graph of the points in points 2 into a plot that I'll call plot of points 2. I can enter that. Doesn't matter that I redid it over the other one. Both variables have graphs stored in them. Here's plot of points 2. Plot of points 1 still has a graph stored in it. That's the straight line. Do you see how those points are on a straight line? If I go to change the 1 to a 2, you should see that the points are not on a straight line. Ready? 1, 2, 3, go. They change. They're not on a straight line. The implied curve is a curve. In fact, it's got a bit of concavity to it. It's called concave up. The slope keeps increasing ever so slightly. Show is a command in Mathematica that combines graphs. What I did a few videos ago is I used the show command to combine the graph of the original straight line in red. You can see I have this option, plot style, arrow thickness, 0.01, comma red in a list, with the black dots that I originally had stored in a variable I called plot of points. Let's now use show to combine the two graphs that are stored in plot of points 1 and plot of points 2, along with this red line for the graph of F1 and say a blue curve for the graph of F2. You can plot within the plot command more than one graph, though you need to put the two functions within a list separated by a comma. I'm going to call it F1, remember, now instead of F of t. It's going to be F1 of 2t. I've got F2 of t in here as well. Let's color F2 blue. So within the plot style option after the arrow, I will put this within a different list, a bigger list. I will copy and paste this code to the right, separated by a comma. These are both in now a bigger list. I'm going to change the red to a blue. Take a look at how this looks. That's the syntax. So the first graph, the graph of F1, is going to be red. The second graph, the graph of F2, is going to be blue. I better change plot of points to a plot of points 1 and then a comma plot of points 2. So I've got three different graphic objects that are going inside the show. I've got the plot of F1 and F2. I've got the dots that are on the straight line, which would be the red graph, that are in the variable called plot of points 1, and I've got a bunch of dots that are going to be on the blue graph, the curve, that are called plot of points 2. Plot label and axis origin, etc. can just go outside of those things. Those are formatting options. I can enter this now, see what I get. Yeah, there I got the red graph and the blue graph. The red graph is straight, that's f1, that's the linear function. The blue graph is not straight, it's ever so slightly concave up. That is the exponential growth function. You can see here then why the blue graph is higher than the red graph, evidently. It's concave up. Ultimately, it's increasing at a faster rate. The red graph at t equals 10, which corresponded to 2020, is approximately at 1.1 million, or 1,100,000. And the blue graph, recall, was approximately at 1.15 million people, or 1,150,000 people approximately. So it was slightly higher than the red graph. Do these graphs agree at all? Ever? Yeah, they agree technically speaking, theoretically at time equals 3, though because they were approximations, there's not going to be a perfect match. If I zoom in with the plot range, this is just a P window here, by the way. The default for this plot range is in the vertical direction. If I create two lists, one for T and one for P, like this, and let's change the P window to go from, say, 700 to 900, that will effectively zoom in near the first 4 points here. This is the T window, 0 to 3. This is the P window, 700 and 900. And we do see there is a slight difference in the graphs on that window. And in fact, the blue graph is below the red graph there. What's going on? This is the fundamental math I'm trying to get across in this video. Remember, these graphs essentially agree at t equals 0 and t equals 3. So in order for that to happen, since the blue graph is really a concave up curve, it's going to have to be below the straight red graph over that interval of time. But then if I go back to the wider interval from 0 to 10 and go up to, say, 1200 here, because the blue graph is concave up after t equals 3, it will be above the red graph. Okay? That's the basic kind of mathematical comparison I wanted to do in this video. That's the main mathematical point, and I reviewed the Mathematica Code. In the next video, we'll go down to the card appreciation example, and we will go back to using Manipulate to make some animations to see what's going on in comparing and contrasting linear and exponential functions.